today we are going to discuss a bit of classical machine learning problems, and maybe the first few slides would be similar to what you already saw in the previous session, but I try to skip them, to go fast through them, but please stop me whenever you have a question. So machine learning paradigm in general, it has many different paradigms. First one, supervised learning, unsupervised learning, reinforcement learning, and sorry, and other. So these three are the main, most famous and well-known paradigms. But other than this, there are many other uh, paradigms, for example, semi-supervised and self-supervised learning, which we will see through these slides. But other than that, we have active learning, meta learning, few-shot learning, zero-shot learning, and many more approaches. So supervised learning is coming from the supervision. That means the data set that we have. So every machine learning algorithm that we are going to discuss, they're talking about some data. When we have the desired output, when we have the labels, when we know what we expect from any input, when we know the expected output, we call it supervised learning. And we teach a model, okay, this is your data, this is the category one, this is the category two, and what would be, and based on that, give me a label or category for the given sample. Unsupervised, there is no desired output or label, so we don't know exactly what is the label for each sample, and we train a model to find the underlying pattern in this data. For example, in the clustering, the model can find similarity between samples based on their shapes or based on their colors or based on other features. This is one approach on unsupervised learning, and the most famous one whenever you see it in presentation, it starts with clustering as an example for unsupervised, but it's not limited to that. For example, we have, sorry, give me a second. For example, we have anomaly detection and other approaches that are part of unsupervised learning. Then we have the reinforcement learning, which comes from the reward. We don't have any label, but we have an environment situation that provides us the feedback. And based on the feedback, we can train the agent or the model. Because in reinforcement learning, we don't call it model anymore, we call it agent. So this is a figure just to show general idea, but in reality, the graphic, the demo to show how it works is like that you have an agent that takes an action. This action affects the environment. Then we have an observer or interpreter that checks the new states of the environment, and based on that gives some reward to the agent and also provides the new states of the environment, and agent takes the next action. Semi-supervised learning is considered a combination of unsupervised and supervised learning. And this is the situation that you have many unlabeled data. You don't have any information about this. You have a bunch of data, but it's expensive or hard for you to label all of them, to find the correct label for all of them to train a model. So what we do, we choose a subset of them, or we find a subset of them that we have the label for them. Then using these two sets of data sets, we train the model. We train first on unlabeled data to get some general idea of how the data looks like. And then with the labeled data, we further improve the performance. Then we have self-supervised learning. This term is recently added to the community because when we have the label, we call it supervised. When we don't have the label, we call it unsupervised. In self-supervised, there is no label, but we find a way to use the data as its own label. So because there is no label, it's unsupervised. Because we have training data labels, then it's supervised. It would be confusing. That's why they call it self-supervised. And as an example for image understanding the image pattern, for what they do, this is only one way of self-supervised learning, is they remove a part of an image and then train the model to guess which of these images are the correct part of that image that is removed. So we have label here, but this label is coming from the data itself. We call it self-supervised learning. And finally, in supervised learning, usually we define two different sets of problems: classification and regression. In classification, we have discrete outputs. We have usually classes, categories that we assign an input to one of these categories that we have. On the other hand, regression is continuous output. It generates a single value, which can be any number, and the use cases is, for example, in the stock price prediction or survival analysis, and many more other approaches. I think all of these you already saw it during your last presentation. Okay. Before continuing, there is one assumption that we need to hold, that we need to consider whenever we are working with machine learning, and this is true for all the machine learning algorithms and approaches that we are discussing through this workshop. We call it IID assumption. The IID assumption says that all the samples in our data set are independent and identically distributed. What does it mean? Independent, that means, for example, I have a list of patients and I want to choose a subset of these patients to create my data set. So when I choose one patient, it doesn't affect the probability of choosing another one. So the samples in our data are independent from each other. Choosing one, working with one does not affect on the other sample. And they are identically distributed. That means the probability of choosing any of these are the same, no matter how we choose, or what is the characteristic of that sample. All of them have the same probability distribution, and it doesn't change when we choose a sample or another one. This is just when we are working with machine learning, we usually use this assumption, and usually this is true. It's not 100% true, but with good confidence, it's true for many of applications that we are going to use, and we can hold. Let's talk about evaluation for a bit before jumping to the main slides. Evaluation is a part that we want to find which algorithm is working better for us. And it's kind of a metric that check, okay, this algorithm 1 or algorithm 2 is better. We want to choose the best algorithm that we want, or we want to see how our algorithm or our model is working in real scenarios. And for that, we need two things: the test data and evaluation metric. So assuming that we have our data set, what usually we do, we choose a subset of this data set and we consider it as a test set. Then the remaining, we call it train set. Further, it's better to also divide the remaining training set into two other subsets, the validation set and another training set. So in general, it's better to divide the data into three parts: the train set, validation set, and test set. We use train set and validation set for training, and we use the test set for reporting the result. And the idea in most of the machine learning are like this. We train a model on a train set. Then we evaluate it on the validation set. Is the result good enough or not? If it's not good enough, we continue the training, we change the model, we tweak the model, we change somehow the hyperparameter of the model, or we try different types of model until we get a good performance on validation set. When we get this performance on validation set, when we're satisfied with the result, when we want to report it in a paper, in a publication, or to the community, then we need to report it, evaluate and report it on the test set, the last part. So here is a very important point, and that is we only touch the test set at very last step. And as soon as we touch the test set, as soon as we see the result and the report and evaluation on the test set, we cannot go back and tweak the model anymore. If we do it, it's kind of a cheating, and our result is not reliable. So we call this tweaking part training phase, which training on train set and evaluation on validation set, all of them together, we call it training phase. And evaluation on the test set, we call it the test phase. Other than test data, we also need some evaluation metric to see the performance of the model. And for evaluation metrics, we need two things. The first one is similarity, the similarity between the predicted output to the expected output. Is it close enough to what we expect from the model or not? And we have many different metrics for different tasks that based on the task that you are going to work on, you can find it and choose it. For example, if it's classification, we have accuracy, F1, recall, sensitivity, etc. For regression, we have MSE, MAE, or R-squared. For machine translation, for example, we have Lewis score. For image segmentation, we have Dice score, and many more. So it depends on the task. Usually we can find a good metric that we can use it. But for example, here for classification, we have many different metrics. Are all of them good for our specific task? So other than similarity, we need the metric to be meaningful. What does it mean? Let's consider this example. So I have a two-class classification problem, and I have a test set of 100 samples. In my test set, 95 of my samples are coming from class A, and only 5 of them are coming from class B. Now, I use a model, which is not a real model. And in my model, it says, no matter what's the input, the output is always class A. Okay, that's a very simple model to not train, to use, or to implement. It's only one line of code. What's the accuracy of this model? It's 95%. So usually 95 seems a good number. We say, okay, my model had 95% accuracy on the test set, so it's a good model probably, but we know that it's not true. We know that our model is not doing anything. So here, accuracy is not a meaningful metric, although it measures the similarity for classification problems, But in our use case, because the distribution between two classes is very different, accuracy has no meaning for us. Let's consider another example. For example, we have again a two-class classification problem. This time it's related to the cancer. We have 100 patients. 50 of them are healthy and 50 of them are unhealthy. So this data set is balanced. The distribution of the two classes are similar. So probably accuracy would be good. But my model, the model that I trained on this data set, out of these 50 healthy patients, predict 49 of them as healthy and one of them as unhealthy. And out of these 50 unhealthy patients, it predicts five of them healthy and 45 of them unhealthy. So if we calculate the accuracy for this model, we get 94%, which again seems good. And the data set is balanced, so we don't have the issue with the previous example. But here there is another issue, and that is the cost of mistake is different for healthy and unhealthy patients. Here, if there is a healthy patient and I say, okay, it's unhealthy, a model says it's unhealthy, nothing bad happens. The doctor goes and check and run more tests and we see, okay, the model did a mistake, that's fine. But in case of an unhealthy patient, if the model predicted healthy, we'll say, okay, it seems healthy, the patient goes home, nothing happens. After a couple of months, we ran into problem. So here, the cost of this mistake is much higher of another type of mistake. So this is another thing that we need to consider while we are doing evaluation and choosing our metrics. Okay, the KNN was not part of the algorithm that we're supposed to stuff, but I just wanted to show you that this exists. Usually we are not using it, but it's very powerful algorithm. So assuming that we have a training data for deciding to go out and playing or do whatever outside based on the outlook, temperature, and the wind. And then based on that, so we go out and we say, okay, that it's good to go out or not, and we record it for many days. Now we want to predict it for future days and see, okay, is it good to go out or not? And the nearest neighbor algorithm try to find the most similar samples from train set to our sample here and do the prediction based on that. For example, here we see that, okay, we have exactly the same scenario in our training set, so probably the best decision here is to going out. Here we have another sample. It's not exactly the same, but it has the most similarity in other situations. So probably we use the same decision that we made in the past. This approach was nearest neighbor. We choose the most similar one in our data set. If we choose, for example, the most three similar samples in our train set, we call it nearest neighbor, or 5 nearest neighbor, or in general, k nearest neighbor. So we need to decide which number for k we should decide to use. There's one more thing that I would like to discuss before jumping to the another topic, and that's encoding. So in order to get the similarity, or in order to work with any machine learning algorithm, we need to convert our data set into the numbers, because computers and algorithms and all of these are working only with numbers, with values, but not with categories or any other thing. So what we need to do, we need to convert these to to some kind of numerical representation. Here we use a very simple approach. For example, for Outlook, We check and we see that, okay, we only have two possibilities, sunny, rain, and cloudy. So we assign a number to each of them. For temperature, for wind, and for even our label, we do the same thing. We see all the possibilities and we assign a number to each of them. And then using this approach, we convert our data set into the numbers. Now we can easily pass these numbers to any machine learning algorithm and train our model to do the prediction. Here we can use mathematical functions to calculate the similarity and find the most similar in our training. Any questions so far? Okay. So linear regression, site also during the previous session, we go over it quickly. In general, machine learning models, they receive an input, they predict an output, and the model itself is a function of the input and some parameters, which usually we call it weights. So it's a mathematical function of two inputs, the weights and the input itself. And it does some calculation to generate the output for us. In case of linear regression, the function is simple, is a linear projection of the input. For example, if our input has m features from x1 to xm, then we have w1 to wm, which we call it weights, and we have a w0, which sometimes we show it with w0, and sometimes we show it with term b, which we use it for bias. And it's just multiplying these values together and at the end adding with W0 or the B value. So that's very simple model. Here is a numerical example. We use dot product for implementation in in algorithms, and then we have the bias and we calculate the output. In linear regression, we try to find a line that is close to all of these numbers. So there are algorithms to train that, and the hope is to find this regression line, which we can show it with this formula W times X plus B. And this is if it's in two-dimensional space, it's a line. If it's in more than that, it's in hyperplane. But then the question is, okay, there are many possible lines. Which one is the best? Which one we should use it and how we should find it? For that, we need to optimize it. And we want to find the line that is close to all points or all samples. That's the best thing that we can do using linear regression. And for that, we define a cost function. We call it mean squared error, which takes the distance, the square error of all all expected output or labels with the predicted output, and then we divide it by the number of samples, and we try to minimize this cost function or this value, this loss function. Here, I want to go over a very simple example here. This is a toy example. This data set is created by myself. So this is a sine function. I just try to have an idea what is the expectation and what are these dots. These 7 dots, 6 dots are how many? 1, 2, 3, 4, 5, 6, 7. These 7 dots are my training samples, and these values are generated from the sine function. I just added a bit of noise to make it more similar to real data sets. So here we can see that at 0, almost 1, almost 2, almost 3, almost 4, we have the sine value, but with a bit of noise added to them. Okay. And if I want to use linear regression in Python, so tomorrow we will have our practical session. We will go to our Python and we implement most of the algorithms that we saw. But it's pretty straightforward and simple. We call it we import the model from the library that we are using. In most of our work, we are using, in most of our classical approaches, we are using scikit-learn, sklearn, scikit-learn library. From that library, we import the model that we want, which is in this case is linear regression. We create an object from that library, and then we call the function fit to train the model. So it's pretty easy and straightforward to use them. And if we do that, it generates a line like this for us, the red line. This red line is the result of training linear regression on this model. But as we can see, this is not truly what we expected. We expected something like the sine function, but it's a single line. What we can do about it? So there are many different ways to deal with these scenarios. The issue is the linear regression model is only able to generate a line or hyperplane. It doesn't have any nonlinearity. One approach is to add nonlinearity to the data itself. And in this case, we use the polynomial features. For example, if I have a value of 1 as my input, and I want to the polynomial degree of 4, so what I do, I try to take the power of 1 to the 0, which is 1, then 1 to the power of 1, which is 1, and the same. So for 2, it would be a bit easier. 2 to the power of 0 is 1, 2 to the power of 1 is 2, to the power of 2 is 4, to the power of 3 is 8. And the same, for example, for 7 is 1, 7, 49, and so on. Now, instead of using only a single value to represent my sample, I use this combination of values which have some nonlinearity. So here I use polynomial, but we can use other nonlinearity to add more complexity to the model. And now train the model based on these values, not only a single value. Let's see what happens. I use the degree of 0 first. And degree of 0 means do not look at anything. It's anything to the power of 0 is 1. So it's the model is actually is y equal to b. So it's a vertical line. It doesn't do anything for us. If I use degree of 1, it's again our input to the power of 1. It's exactly the same approach that we had. And it generates a single line for us. But if I use the degree of 3, so now my function, my line is like this. It has some polynomial nonlinearity in it, and it can predict it better. And as we can see, it was able to almost guess a line similar to the sine function, to my expectation. So it's much better. But let's increase this degree of polynomial and see what happens. If I go with 5, so I switch between the previous slide and this slide to see it a bit better. Here, degree of 3 is close to my samples, but it's not exactly the same value. Okay, here is very close, here is very close, but the others are not exactly. When I use degree of 5, it gets much closer to the sample, so it seems okay. It's apparently better. But as you can see, this is a bit further from the sine function that I expected. In the previous sample, it was closer to actual line, but in this sample, it's a bit further from the actual line, but it's passing exactly over my training samples. And also here, it has a weird shape, which is not what we expected. But that's fine. Let's increase the degree again and use degree of 10. Now, the model was able to predict all the sample exactly as what we expected. But the shape of the model, it's not related to the sign function at all. So what happened here? This is one of the things that we need to, one of the consideration that we need to have when we are working with machine learning, because many times we get a very low loss function, a very good performance. For example, here, if I use these samples as test set, I see that, okay, the performance is 100. It's exactly what we expected, but the actual model is not good at all. So for that, we need to identify the errors. Sorry, sorry about that. So we have two source of error. We call it bias and variance. Just to be a bit more deep, we use the term bias in previous slides. We use the term bias in the previous session as well. This is a bit different. But here in machine learning, we have two sources of error, bias and variance. Bias error is coming from a simple model, a simplistic assumption in our learning algorithm. So it says, okay, the model is very simple and it cannot capture the only underlying complexity or pattern in our data. The other one is variance. Variance is when the model is too complex or very sensitive to the data, to the fluctuation of the data. And usually it captured the noise, captured the fluctuations instead of learning the underlying pattern. And if we go back to our previous example, exactly here, what happened? It was learning these noises, not the underlying pattern that we expected. So considering these two, we see that, okay, if we have a nonlinear data and we go with a linear line to do this prediction, the model is too simple. We call it, in this scenario, we have high bias. Usually we call it's the model is underfitted. We have underfitting problem here. We cannot find a true capture. On the right hand, we have high variance, a very complex model. The complex model, instead of learning the general pattern, is trying to memorize the sample. It's learning the noises in the samples, not the pattern itself. In this scenario, we call it we have high variance, or we call it we have overfitting issue. And the best scenario that we can have is to find a middle complexity. So here on the left, it's too simple. On the right, it's too complicated. Here is the probably best thing that we can do, so that we have both low bias and low variance, and we have a good fitting almost here. We almost were able to capture the general structure of the data. And we have the same thing in classification problem. If you have a data like this, then a single line might seems good, but a curved line would work a bit better. So a simple straight line would we call it underfitting. It's too simple. Here we have a complex model. It's overfitting. It memorized all the samples, not learning the pattern. And the best thing is something in the middle, not too complex or not too simple. And this is one of the things that we need to pay attention to when we are training a model. And for all of overfitting and underfitting, there is there is one approach to help us to understand it. Okay, do we have underfitting or overfitting or not? And that's to compare the performance of the model on the train set and test set or validation set. If the error of train set and validation set or test set are close to each other, that's a good thing. But if they are far from each other, it's not a good thing. So if the performance on train error is very low, but on the test error is very high, so there is a big difference between the performance of these two, it's not a good model, and we call it overfitting. Here, the performance of these two are very similar, close to each other, but the performance is not good in general. So here we call it underfitting. And the optimal solution that we are looking for is something in the middle, that the both test error and train error are close to each other and both are low. So here, if we look, the train error is lower than here in the middle, but it's not actually a good model. So if we only look at the train error, we may choose a model that is not right for us. And this shape is based on the complexity of the model, similar to previous shapes. So here the model is too simple. Here the model is too complex. In the middle, it seems the best. So we need to find the middle point here. If there is no question, I would like to go to the next topic. See the chat. Okay, good. Now we'll start our new topic for today, SVM or support vector machines. But let us start with a simple question. So if I use a linear regression to find the decision boundary between the red dots and blue dots here, because there are some randomness in the model, based on this randomness, our model may choose one of these lines here. But which one of these is better? So all of them, they have zero error on this data set. All of them seems good. But is there any difference? Is there any preference between these lines? So logistic regression cannot, or linear regression cannot find which of these is better for us. And hence we use SVM, it's called support vector machine. So the idea of support vector machine is not only to find the line that separates the red dots and blue dots. It also specify a few points in our training data, and try to find the line that has the largest margin with all of these sample points. So it finds a few sample points, call it support vector, and based on those, it finds a line that has the largest margin. So this way it can find the most optimal solution. So in this case, from this perspective, SVM is much more powerful compared to linear regression or logistic regression. In terms of implementation, in scikit-learn, again, it's very easy. We call the linear SVC, here they call it SVC, from the library, and then we create an object, and then we do the prediction or the fitting part. So that's pretty straightforward. But just to remember, scikit-learn has many different implementation for SVM. It has linear SVC, linear SVR. SVC is for support vector classification. SVR is for support vector regression. So we can use SVM for regression, and both regression and classification. And there are many other approaches. So this SVC that we have it here is a more general function. So it has more features and complexity. If we choose SVC, and then we specify the kernel as linear, which we talk about kernel in a bit. Specify the kernel as linear, it would be exactly the same as linear SVC in terms of use cases. So just a quick reminder, tomorrow we will go over them. But if you search for scikit-learn SVM, you may see many of these. And based on that, on your problem, we first need to find, okay, are you looking for classification or regression? And then probably go with SVC or SVR. Those are more general functions. Before continuing, let's consider these two examples. Here, I have a data set that with a single line, I can easily separate the green samples from the red samples. The straight line, I can use SVM, I can use linear regression, logistic regression to separate these two. So pretty easy. But there are some other cases, and usually this is real world data, that they are not linearly separated. There is no way I can find a single line that can separate the reds from the green one. What we can do here is, logistic regression and SVM, both of them are linear. The only thing that we can use is to add nonlinearity to the feature space, like the polynomial example that we saw in the previous previous slides. With that nonlinearity, we add more complexity to the model, and probably the model can handle that. But SVM also has the kernel. It's similar to adding nonlinearity to the features exactly, but it's done through the SVM itself. And the general idea is we have an input space which is not linearly separable. Then using a kernel function, we transform these samples to another space with another sets of dimensions, which in that dimension, they are linearly separable. And in that case, then we can use SVM to solve this problem. So SVM is a linear model itself, but using kernels, we can add nonlinearity to this model. In scikit-learn, we have three different sets of kernels that we can use. Polynomial is exactly like what we saw. We can either use the polynomial feature here, or we can add the polynomial by ourselves. We have the sigmoid kernel and RBF kernel. And in this case, we can see, okay, that we can see the data set, and we have some general understanding of how this kernel works. Linear kernel means no kernel. As we can see, it cannot separate the data from each other. Polynomial here is not working very good. Sigmoid here is working much better, but exactly it has some mistakes here and here. But RBF kernels, it's been shown that in many, it's okay. In many cases, the RBF kernel is working good enough for us. So if you are not sure which one to choose, probably RBF is a good option to start with. But consider that the choice of kernel is another hyperparameter. I forgot to talk about hyperparameter. Let's go back to one of our slides. Okay, consider this example. This A, A5, A4, A3, etc., and B, these are my weights in, for example, linear regression or any model that has this kind of parameters. We call them parameter. Parameters are those that is trained and adjust during the training process. So the algorithm that we are using finds the correct value for these weights. Okay. But the algorithm cannot decide which degree should we use. The choice of this degree, we call it an hyperparameter. So we choose the hyperparameter, and the model finds the correct value for the parameter. So we have two definitions: parameters, the one that is learned by the model, and hyperparameter, the value that we choose. And choosing the value of hyperparameter is based on the performance on the validation set. So here, the choice of kernel is a hyperparameter. That means in this example, we saw that, okay, RBF is working pretty well in this example, but that doesn't mean it's working well on all scenarios. So we need to test and try different kernels to see which one is working better for our use case. So the choice of kernel is a hyperparameter. So the examples that we saw already for logistic regression and SVM, it was able to find a single line, and it's useful when we have only two classes to find it, to make a decision between two classes. But what happens if we have more than two classes? Can we use this model? Yes, there are two approaches. One of them, we call it one versus one, and the other one, we call it one versus rest. In one versus one, for each combination of these, every two samples, every two categories, we train a classifier. For example, here, I train a classifier to classify between reds and blue, which is this line, let's say, which is this line. Then for classifying between blue and yellow or orange, I train this line to distinguish between these two, and the same another line for red and orange. So we train for any combination of two of all our categories or classes. And the other one is one versus rest. This time I train a model that for example here for blue, to only classify blue, and we consider the rest as a single class. So I create a data set that one class is blue and the other class is the rest. Then I train a line. I do the same thing, for example, for orange. One class is orange and one class is the rest. And the same thing for all classes. So there are two approaches. Which one is better? It again depends on the scenario and on your specific problem. And each of these two have their own issues. For example, here in the middle, it's not easy. Okay, which category is in the middle? Is it blue, green, or orange? Because this line says, okay, it's not blue. This line says, okay, it's not green. It's not red, and this line says it's not orange. So we have this issue with both of these approaches, and we should see through validation set to see which one is better for our cases. But in general, one versus one, we need a combination of two classifiers. But here in one versus red, we need only n classifiers, where n is the number of classes or categories. So one versus rest requires fewer number of classifiers. One versus one is better for more balanced data set. It's better for handling of nonlinear scenario, and it has issue and complexity in voting in those areas that we are not sure which label it belongs to. On the other hand, one versus rest, it's lower number of classifiers, it's more simple, and because of that, it's more efficient and faster, and it's able to work with imbalanced data set as well. So I didn't stick here. It's not able to work with imbalanced data set. It's an issue with that, which is the data set is imbalanced. Let's say you have 20 samples then five categories, each 5 categories, each category four samples. Then if you go with one versus rest, you are training a model that has, let's say, 5 positive samples and then 15 negative samples. So the data set that is training on is imbalanced. So that's one issue here. But for one versus one, it's more balanced. And in terms of scikit-learn, you can use these approaches for any two-class classification model. So for example, here we are using linear SVC. So what we do, we call this one versus one classifier from multi-class of scikit-learn. Then we pass this linear or any model that we want to this one versus one classifier. So what it does is train bunch of these linear SVC for us for all of the classes. Or we can use one versus rest classifier and do the same thing. In case of SVC, if we use this function, so the approach in the top, we can use it with any model, SVC, linear SVC, linear regression, logistic regression, etc. Any model that we have decision trees, which we will see. But the SVC itself has a variable that we can choose between one versus one or one versus rest. And if we choose any of these, the output of the model would be based on that. But there is a point that you need to consider, that the training of SVC would be only one versus one. You can choose how to show it to you, but the training is only one versus one. So if you want to use the training one versus rest, you cannot use this variable to set it. Okay, now let's go to decision trees, the next sets of algorithm that we are going to talk. Decision trees are pretty simple and straightforward to learn. And we are using this kind of decision tree not only in machine learning, everywhere. So there probably all of you have these kind of charts in your organization that based on some condition you choose to do what to do in the next steps. And this kind of decision-making process is existing everywhere. In machine learning, we use the same approach. For example, here we can, based on the data that we have, it's similar to the example that we saw, we can design a decision tree that decides, okay, should we go out or should we go out to play or we shouldn't. And for example, here in this decision tree, it first look at the output. If it's rainy, it says, okay, don't go out, don't go for playing. Doesn't matter what's the situation with wind or temperature. Don't go out. Then it checks, but if it's cloudy, then it checks the wind. If it's strong, it doesn't go. If it's not, then it suggests to go out to play. If it's sunny, then it's look for the temperature. If it's hot, don't go. If it's cold, then again it checks for the wind situation. If it's strong, don't go. If it's weak, go. So these combinations, as you can see here, for wind, we are checking it in two scenarios. If it's the temperature is high, based on the temperature or based on the outlook, may have we have multiple checking of the wind. So this is the general idea of how the decision tree works, but the training is simple as, but what we do, we start with the root, we choose one sample for the root, for the beginning. one of the feature at first. What we choose the feature at first? Sorry. We choose the most informative feature here. And how we find this most informative feature? We go to the training set and we see, okay, if I choose based on Outlook, I can easily eliminate bunch of samples in our training set. So if I go with Outlook, it's much easier. But for example, here, look, if we go with temp, I have to check other features as well. So we use the most informative feature. Finding the most informative feature, it has mathematical formula for that. There is no need to implement anything, but here we only look at, we will just go over these approaches to see what happens underlying of this training algorithm. So when we choose the most informative feature, then we go and assign labels to each of these values. And then if all samples in that part, they have the same outcome, so it's an end node, we call it leaf. Or if it's not, if we have different values, different categories, then we use another informative feature to continue. Then for the other one, the same thing. And we continue until either all the values, all the nodes and nodes are leaves. Here, everything is in the same category in our decision tree, in our training set, or we define depth. For example, depth of 1 here, depth of 2, depth of 3, and we define a max depth, and we stop when we reach that max depth. In terms of the training loop, we can see that, okay, it's here. We start at the root, we select the most informative feature. We create the child nodes of the root based on the feature and the partitioning of the data based on the categories that we have. Then we continue the same thing for each of the child nodes. We repeat the same process. We choose the most informative and we continue the same until we're reaching the end criteria. Usually we have max depth criteria, or if a node is a child, is a leaf, and all the samples in that partition are in the same class. There are a couple of hyperparameters for decision tree in scikit-learn that we need to consider. The first one is criterion, is the information gain, is the one to choose the most informative feature that we talked about. There are two possibilities here that you can use Genie or another one. The max step that we talked about, how to stop, when to stop dividing and creating more branches, so not to make it so complex. And there are other hyperparameters that it's not in the basic definition of this decision tree, but you can also define it in the scikit-learn. For example, you can have minimum number of samples to have a split, otherwise you don't go for a split, or minimum number of samples to have a leaf, or maximum number of features that we want to go, and many more of these hyperparameter in scikit-learn. But the most important two are the criterion and max depth. Max depth to train the decision tree. Okay, let's have a very simple example here. I have a data set of only two samples, a red dot and a blue dot. Okay, and I want to train a decision tree based on that. Here, when I train a decision tree, I use it says, okay, I use X1. It has two features, X1 and X2. If it chooses X2 as a feature, it cannot distinguish anything. So the Gini, as a criterion, we are using Gini. It uses X1. It says that X1 is the most informative feature because if I choose X1, I can easily separate these two samples from each other. And it says, okay, if it's X1 lower than 0, then go for one sample. If it's not lower than 0, then go for another class. And if we paint the decision boundary of this tree, we see that, okay, all the samples in this area are one class, and all the samples in this area is one class. So it was easy, the model is working, train, everything is fine. But let's consider another example. Here is the data that we have. As we can see, it's not easily separable with a linear line. So probably we cannot use it linear regression, logistic regression, or SVM without kernels. But what about decision tree? If I train a decision tree, it's even with very high number of max depth, then this would be the surface. This would be the decision boundary of my tree. If I'm not mistaken, for this prediction, I used max depth of 10. So as you can see, it cannot find the real boundaries between these blue and red points. So what should we do here? How we can use decision tree to overcome this issue, to solve this problem? One approach in machine learning, it's not only related to decision tree, it's called it ensemble. When the model is not able to get a good performance, and when a single model is not good enough to get a good performance, what we can do is we can train bunch of models on the same data set and then merge the result of these models. It's like, okay, probably for a problem, a real life problem, maybe one person can make a decision, but if three people sit together and think more and make a decision together with voting or other approaches, then probably they make a better decision. So this ensemble is almost the same idea, similar idea. We train a bunch of different models and then we merge the result. For merging the result, the simplest approach is getting the majority voting. For example, out of 5 models that I trained, if 3 of them gets the same prediction, I will choose that. I take the vote of all of those and I choose the labels based on the majority voting. This is the simplest one, but it's not the only approach. Here we can train also a meta learner, we call it here, that based on the feature from data, choose which model to use this time. So maybe it uses a combination of a subset of this model or choose only a single model. There are many different approaches for merging the result, but the simplest one is the majority voting. Also, for training these models from the data, there are a few different approaches. So the simplest one is to train all of these models on all of these samples in the training data. That's easy. In many cases, we are doing the same, but there are other approaches for that as well. For example, one approach is to choose randomly a subset of data to train model one. Then, sorry, there is a typo here. This one was model two. Then choose another subset for model two, then choose another subset for model. And that's one approach. Then in choosing these subsets, there are different approaches. For example, choose the subset. The samples that is used to train for model one should not be used for to train model two, etc. All of these combination of these selection samples, they exist and they have different performance on different problems. So this is one thing that you should consider if you want to use ensemble. So we call it bagging, bootstrapping, and etc. These approaches, and usually we use when we have a very simple and simplified model, but we want to use it for a complex problem. So usually with this approach, we can get a higher performance. But in case of decision tree, there is another algorithm which we call it random forest. It's a combination of an ensemble of bunch of decision trees. If I train a sample random forest with only one tree, then it would be exactly one decision tree, the same example that we saw in the previous slide. If I use train a random forest with four trees, I get a better result, but it's still missing some points. But if I train a random forest with 32 trees, then I get much better prediction. And as you can see, the random forest was able to find the real pattern here, the underlying pattern of the data, and was able to classify all the samples, most of the samples correctly. So there are a few points here that are not accurate, but it's almost was able to capture the underlying representation. Okay, this was the last slide for classical machine learning before we jumping. If you have any question, I'm open to that.
Hey, Farhood. I guess like I'll ask you a quick question. Do you hear me, by the way?
Yes, yes.
Yeah. Um, is there a limit on the number of data points that you have that would limit the number of random forests that you pick? Sorry, the number of trees in the random forest that you pick. So how much data do I have? Like, for how much data can I pick the maximum number of like random forests without overfilling?
Uh, I don't have answer to that, accurate answer to that. I have to check it. Uh, the random forest, it's not on top of my head. What is the approach of choosing the subset in the data to train each of these trees? Uh, but it's not in terms of implementation, it's not limited, so you can go much further than that, much further than um, the number of samples. For example, if you have 10 samples in your training set, then you can go with 100 random with 100 trees for your random forest. In terms of implementation, there is no limit. But then the number of limit that the limitation that you have in terms of overfitting, it's not overfitting, I would say. But the thing is, many of these the trees would act similarly because they don't have different combination of the data. I think they are using bagging. That means they use a subset for each of these models, then they use another subset. So the number of subsets in your data is kind of the limitation that you have, the possible number of subsets from the data that you can, which is 2 to the power of number of your samples. But that's not the only thing, because then there is some randomness in decision trees as well. So in the more complex scenarios and in the number of features, there is a chance that, or you can go with multiple decision trees based on, it would be higher than only using scikit-learn. Then it's not only training a new decision tree based on the subset of samples that you're getting. For example, on the same subset, then you can go with different max steps, or you can go with different criteria. So you can make more variation of decision trees to have more decision tree and have a larger number of models for your ensemble. So it's not limited to that. It's only the number of possible uh, subsets, and then you can increase that capacity by adding more by considering different hyperparameters for each model.
Thanks.
Eugene, if there is no more question, I would say that we go for 5 to 10 minutes rest, and then we go for the other set for the neural network.
Yeah, sounds good. Say 10, come back or something.
Okay, so we would be back on 9:55.
55, okay. All right.
Okay.
See you guys soon.
Shall we start? Okay, Agent, let me know when should I start.
Yeah, go ahead.
So in the next part, we are going for neural network. But before going that, look at this shape. This is almost the same as linear regression. So we have bunch of weights which multiplied with the inputs. Then we add all of these together. Then we add the bias, sum everything together. And this is our output. So this general idea, if we say, okay, y is equal to a function of x and weights of input and the weights and parameters, then we can look at it into that different. If we use identity function, or we don't use any function, like here, it would be linear regression. If we use a sigmoid function, so as f, we use a sigmoid function, it would be logistic regression. If we use a step function, we will see what is a step function. It's 0 if the input is lower than 0, if it's 1 if it's greater than 0. If we use a step function, then we call it perceptron. Perceptron is the previous generation of a neural network. And in general, if for any activation with this function, we call it activation function. For any activation function, we call it an artificial neuron. So the general idea is very similar, but on the other hand, the idea of the setup is very similar to the biological neuron. So in biological neuron, from the dendrites, we get some signal from the other neurons, and then if the sum of all of this signal is higher than some threshold or with some biological function inside the nucleus, it decides to pass the signal or generate a signal to go to the other neurons or not. So send a pulse to the other neurons or not based on the input signals from the previous neurons. So the idea of artificial neuron or artificial neural network is very similar. So we multiply input by some weights. So these inputs are similar to the axon from another neuron, or x1 another neuron, x2 another neuron. And then this W, which we multiply it to each input, it acts kind of as a synapse. So how much of this information should go to the cell body, or we use if it's greater than 1, use more if it's lower than 1, use a part of this information, then add all of these together. And if you have any bias, add it together and then apply an activation function. So this activation function either pass this output or not. For this activation function, we have many different choice. For example, we can use a sigmoid function, which is very similar to a step function. If it's lower than a value, it would be almost zero. It's not exactly zero. If it's higher than some value, it would be close to one, but not actually one. And it's a value between 0 to 1 for the middle part. Then we have hyperbolic tangent, which has a similar shape almost, but the output is between -1 to 1 instead of 0 to 1. So these two were the most famous and maybe the only two that we were using in neural network. But from 10 years ago, we started using some other functions, usually ReLU. ReLU is the simplest form in its own family, and it's a max function. If it's lower than 0, then 0. If it's greater than 0, the identity function. So this is so simple, but all of these are adding nonlinearity to the model. And recently, we usually use ReLU or a variation of ReLU. We have many more activation functions that we can choose from. For example, GELU, Gaussian error linear unit, which is Gaussian error ReLU or exponential ReLU or etc. All of them are a family of or similar function to the ReLU. Or we have hyperbolic tangent or sigmoid function or soft plus, many of these, but usually we go with Gaussian error linear unit or some other function. So this is again the hyperparameter that we choose. But before continuing to artificial neural network, I would like to talk about perceptron. Perceptron, as I mentioned earlier, it's a previous generation of neural network. Sorry, it's a previous generation of neural network. No one is using perceptron anymore. More than 67, maybe around 60, 50, 60 years. No one is using perceptron, and there's no need to learn it, but it gives us some idea of how in general neural network works and how in general we train them. So that's why I'm showing it here. So perceptron, the neuron itself, it's